Good morning. Good morning. Hope all is well. Hope everyone is doing all right. Mhm. Good morning. Good morning. Got a few people still trying to come in. So, as always, try to give everybody a chance to get connected before we get started. Good morning. Good morning. Good morning. Happy Valentine's Day to you as well. Happy Valentine's Day to everyone. Appreciate it. All right. So, just trying to make sure. Yeah, so we closed out 5-2 last class. And so we should be looking at 5-3 today, starting with 5-3 today. I think we have 4 sections in this class, in this chapter 5. Let me see. Yeah, awesome. Okay. All right, so 5.3, associations in categorical variables. So we're going to reference that table in section 5.2. So, we'll go back to that. Well, we're looking at conditional probabilities, probabilities of an event that are affected because another event has already occurred. Sorry about that, I had to sneeze. So we have symbolism for it. Probability that A occurs given that B has already occurred. My pen is right here. That's the symbolism. That line, excuse me, that line just represents given that. So the probability that event A occurs given that event B has already occurred. All right, scrolling up. Of course, if I go up too high, you let me know in the chat or unmute. Okay, so the way we'll calculate the probability that event A has occurred given that B has already occurred is by these two relationships right here. They're pretty much the same thing, but it just depends on what information you are given. So if we have a chart that has just the numbers of those categories, like in the chart that we have from 5.2, we'll be looking at the number. But if we actually have the probabilities, you can place the probabilities and set them up in the same fashion. So in the first one, the probability of A and B over the probability of B, or the number of items or objects in A and B over the number of items in B. All right. Are they good? Okay, first one. Suppose a person is chosen randomly from the chart. What is the probability a person has less than a high school degree, is married? So what's the probability a person has less than a high school degree, is married? So you can see the way this would be positioned. Basically, the person that's chosen is married, given that they have less than a high school degree. So that would be the positioning that we would put them, because remember, the position of these matters in reference to that line. So we're talking about the person is married, given that they have less than a high school degree. All right, there go the formula. All right, are we good? Yep, no problem. So going back to that chart, remember that chart was in 5.2. We're looking at what we would need, the number of people that are married and has less than a high school degree, and then the total number of people that have less than a high school degree. So if you go back to the chart, let me erase some of this stuff. All right, so less than high school married is 70. Then the total number of people that have less than a high school degree is 125. So it should be 70 over 125. Went back down too far. Here we go. Yep. So 70 over 125. And then once again, Math Lab let you know whether they want a fraction or a decimal. Anybody questions? Can I scroll up? Now here, I was just showing you the other way. If we want to do probability over probability, instead of just taking the numbers of the categories. So what happens is the probability of being married and having less than a high school degree is 70 over that 665. Remember, 665 is our total number. That's our sample space. So you place that over that. And then probability of getting someone that has less than a high school degree is 125 over that 665. And then if you were to do the work, dividing it means you multiplying by the reciprocal. Those 665s will cancel. And that'll leave you with the same thing as 70 over 125, but give you guys a chance to write. All right, questions on what we did there. Like I said, that was just the other way of doing it. Don't necessarily have to do it that way if they give you the numbers like the chart did. but I'll just show you the other way. And scroll up. Okay, so here, just continue with the rules. Notice it says rule 5. So the last time we had a rule was rule 4, and they just continuing those rules throughout the chapter. So we just finished being introduced to this relationship, and what they were doing here is just another form of the relationship is solving it and having this on one side by itself. So you multiply both sides by the probability of B. And so it's just showing you just different ways you can use this same relationship. That's all. So if you know the probability of A, given that B has occurred, if you multiply that times the probability of B, that would be the probability of A and B. And we're going to use that in a second, but they go into dependent events to give you an official definition. So dependent events are events that are associated, events that have conditional probabilities that change depending on different conditions. Independent events are events that are not associated, and the conditions of one event does not affect the probability of another. All right, so here, if events A and B are independent, then the probability of A given that B has occurred is just the probability of A. Because B does not affect A occurring at all. Mhm. Hold on 1 second. Trying to think, is this the first time we've done cards? Just making sure. So before we get into this next example, just want to make sure. I'm not sure if I did this for you guys, but just want to be sure. So standard 52 card deck. Standard 52 cards means no jokers. Characteristics of our standard 52 card deck will be the fact that we have 4 suits: spades, clubs, hearts, diamonds. There are 2 black suits, which are your spades and your clubs, 2 red suits, hearts and diamonds. Suits is just a category of cards that we'll have. So 13 cards each suit, be 3 face cards, 10 regular cards. Face cards are king, queen, and jack. Regular cards, ace, and then 2 through 10. So your ace is not a face. Give those a chance to write it. Who haven't yet? All right, anybody still holding on to this? All right. All right, suppose we have a standard 52 card deck. Are the events, the card is a diamond and the card is red independent? If you found out another player holds a red card, do you want to know if he has a diamond? So basically you want to check, are they independent? And let me see something real quick. Okay. So I give you a chance to write it down before I keep going. All right, so suppose we have a standard 52 card deck. Are the events the card is a diamond and the card is red independent? So basically we want to know, if you find out another player holds a red card, do you want to know if he has a diamond? Does it matter? Because if they're independent, then it doesn't matter. If they aren't independent, then it would be to your benefit to know. So now we're going back to this idea right here. Yep, I have my wrist on. Hold on. Put that back. So going back here, and what dictates whether they're independent or not mathematically, if you want numerically, is that when I calculate this and I calculate this, if they are the same thing, that means that the events are independent. If they give me the same probability, if they are equal, that means they are independent. So that's what we're going to find out. So first thing we do is find out the probability of getting a diamond. So what we're looking at is next after that, the probability of getting a diamond, given that the card is red, because that's what we're talking about in that second statement. If you find out another player holds a red card, do you want to know if he has a diamond? So First thing, we find the probability of getting a diamond, and that's 13 out of 52. There's 13 diamonds in the deck, 52 cards in the deck. So 13 over 52, that's 1 over 4. Mhm. Then next, the probability of getting a diamond given that the card is red. All right, don't want to go too far, let me know. All right, so first we have to look at the top number, the probability of getting a diamond and red. So all of our diamonds are red. So that's 13 over 52. Then the probability of red cards. Don't forget there are 26 red cards. We have diamonds and hearts, 26 red cards. So that's why this is 26 over 52. And that simplifies to 13 over 26. Those 52s cancel just like on the last problem we had the 665 that canceled. And that reduces to 1/2. So before we go further into the explanation of what we have, questions on what we calculated. All right, so in the green, just re-emphasizing the fact that we had 26 red cards, that's where that 26 came from. So in the blue, we see since the probabilities are not equal, the events are not independent. Remember, in order for them to be independent, we needed those probabilities to be equal. This means that knowing that someone has a red card is useful in determining if that person has a diamond. All right, any questions before we look at the next one? All right, so this time we have a card that is face down. This time you want to know if your opponent has an ace. You discovered he already has a diamond. Is this helpful? Basically, you want to know, are the events independent? All right, so first thing we want to do is find the probability of an ace. There are 4 aces out of the 52 cards, so that reduces to 1 over 13. All right. Now I want to know the probability of getting an ace, given that you know your opponent has a diamond. So given that he has a diamond. All right. So the probability of having an ace and a diamond. So it's only 1 out of 52. It's only 1 ace of diamonds. And then you place that over the probability of all diamonds in the card. I mean, the deck. That's 13 over 52. Those 52s cancel, leaving us with just that 1 over 13. Any problems? Any problems? All right, so conclusion, since the probabilities are the same, the events are independent. This means that knowing someone has a diamond does not help you determine if they now have an ace. All right, any questions? All right, rule 5C. So this is just another variation of that 5th rule. It says if A and B are independent, though, if A and B are independent, then if you want to know the probability of A and B, you just multiply the probabilities together. So we have supposed that 51% of all babies born in the US are boys. What is the probability of a family planning on having 2 children will have 2 boys? All right. So these events are independent. Having a boy one time does not affect you having a boy the next, or a girl, or vice versa. So these are independent events. So if the percentage or the probability of having a boy is 51%, 0.51, where when it always convert to a decimal before you do your calculation, then the probability of having a boy first and a boy second would just be multiplying those probabilities together. That's because, once again, we established that they are independent events. One does not have anything to do with the other. So we can just multiply them together. And that'll give us 0.260. All right. So what about a boy first and a girl second? All right. So boy is 0.51, girl is 1 minus 0.51, which is 0.49. So we multiply the fact that we have a boy, then multiply probability of having a girl, which is 0.49 times that 0.51, and that'll give us 0.2499. All right. Questions? Any questions? Next one, toss a fair coin 3 times. A fair coin is equally likely to land up either side when tossed. What is the probability that all 3 tosses are tails? All right. So once again, our events are independent. Probability of getting tails is 50% or 1/2. And there's just a walkthrough on that. We have 2 options in our sample space, which is heads and tails. Tails is just one option that's in that event. So that's where you get 1/2 from. We're done with the black. And then in blue, we see how we get our answer. You know, if you're talking about getting tails 3 times, then that's 1/2 times 1/2 times 1/2, which is 1/8. All right. Next one, still leaning on what we just finished doing. What about 2 heads and 1 tail? Let's see something. So if problems given, it will tell us the independent. No, you make that declaration of whether it's independent or not. So you have to examine what it is that you're dealing with. So in this case, we're talking about flipping heads or tails. Does the fact that you flip tails, land tails, does that have anything to do with you landing heads? And the answer is no. Like, it's not like if you land tails, then landing tails is not an option for the next event. So it just depends on the scenario you're given. Now with this, when it came to what we were doing up here, it's not that easy to make that determined. That's why we had to go through the formal and figure out, okay, are these probabilities going to be the same? If they are, then they'll be independent. But when it comes to flipping a coin or rolling dice, it's a fair coin. It says equally likely that it's going to land tails and heads. When you hear stuff like that, and then like I said, if you just examine flipping a coin, the fact that I landed tails first has nothing to do with me landing tails the next time or landing heads the next time. So that's what dictates whether it's independent or not. Yes. Yep. Yep. More than likely, they're not going to tell you that they're independent or dependent. Yep. No problem. All right. So here's where we are. What about landing 2 heads and 1 tails? Well, we know tails is 1/2, and if tails is half, that means heads is the other half, right? And so that's still going to give us 1/8. So you're talking about heads 50%, heads 50%, and then tails. It's also a 50% chance of getting it. So 1/2 times 1/2 times 1/2 will still give us that 1/8. Any questions? All right, so let's look at 5.4, last section in 5. So finding empirical and simulated probabilities. Empirical probabilities are probabilities based on carrying out real life random actions and observing the relative frequency that an event of interest happens. All right. Finding empirical probabilities can be slow and laborious, and for this reason, it is often useful to perform a simulation that can be carried out rapidly. Simulations can also be helpful when a simulation is too complex to find a situation, excuse me, is too complex to find a theoretical probability. All right. So looking at the example, we wish to know the probability of getting exactly 2 heads if we flip a coin 3 times. To find the empirical probability of this event, we flipped the real coin 3 times and noted whether or not there were exactly 2 heads. We repeated this for 5 trials. We're looking at the results. So noticing the results 3 times is when 2 heads occurred. All right, so it says, what is the probability of getting exactly 2 heads and 3 flips based on this data? It's 3 out of 5, which is a 60% chance. All right, can we scroll up? So the next things that come to mind, or questions that should come to mind whenever you're doing any type of experiment research, is why is this important? Why can't we rely on this probability? And why can't 5 trials be enough to determine a dependable probability? All right, the reason being is because of the law of large numbers. It's a theorem that tells us that if our simulation is designed correctly, then the more trials we do, the closer we can expect our empirical probability to come to the true probability, which is the theoretical probability. As we approach infinitely many trials, the true probability and the empirical probability approach the same value. All right, so an example of that is flipping a coin, landing tails. We already talked about calculating or how we would calculate that probability. But the difference between the empirical probability and the true probability, or in other words, the theoretical probability, if you were to flip a coin 10 times, and let's say the result was 7 tails out of the 3 heads, that would make the empirical probability 7 out of 10, which is 70% chance of landing tails. But the true probability is 50%. And so what the law of large numbers is saying is that if the coin is flipped more times, then the probability will come closer and closer to that 50%. So the more and more you do it, the more heads you will record, the more tails you record, and eventually you'll get closer and closer to 50%. So that's why a small sample size is not the best way to go about obtaining your probability. You have to do more and more values. And so that's why simulation, whether it be computer simulation or something along those lines, would be beneficial to you to run it infinitely amount of times. So simulations are normally done by some type of program or application or technology. All right, so what if my simulation does not give the theoretical value I expect? There are two possible explanations. One is that your theoretical value could be incorrect, could have miscalculated. Two, it's possible that your empirical probability is varying, or just do more trials. Especially when you go back to flipping a coin, you could be on a string of heads, being repeated, or you could be on a string of tails being repeated, and things just haven't leveled out yet. All right. And that is it for 5.4, which means that is it for chapter 5. All right, so questions on anything I've said, anything I've written. So you see section 5.4 is just summarizing what we did. So it shouldn't be any, much or if any calculation in 5.4, section 5.4. But it'll probably ask you some of these statements that I wrote up here. Okay. So questions on anything that I've written up to this point? All right, everybody good? Everybody okay? Okay, so this is a good stopping point. I'm not gonna just jump into another chapter just because we finished. Now, our third test is 5 and 6. So we'll talk more about not due date, but we'll talk more about, setting it up and all that stuff when we get close to finishing our chapter 6 or whatever. But there's no test coming after 5. We did our first test was 1, 2. Second one was 3, 4. And so the next one will be 5, 6. Okay. So any questions on anything before we close out? Is everybody okay? All right. Okay. So take advantage of your time. Notice I'm not trying to push it because we easily could jump into chapter 6 today. But like I say, I believe this is a good spot to pause, give you guys a chance to get into chapter 5 and try to close out chapter 5 before we jump into another chapter. And so, yeah, so we'll go from there. Next class, we will start on chapter 6 and I'll address any questions that you guys may have generated. So outside of that, you guys have a good one. Take care, and I'll see you next class. All right, thanks. You do the same. Take care.